Hey guys, I hope you're all having a great day. This video is going to be a walkthrough of one of the problems posted under the example homework module on the course website. I am going to be walking through the overleaf version of this problem and writing my solution in LaTeX, but it's also important to note that there is a PDF version of this problem and both of the problems available if you click this problems button on the course website. You can download this PDF, edit it, and otherwise fool around. But for this video, I will be working with the overleaf version of this homework. Hopefully by the end, you guys feel a little bit more comfortable with overleaf, a little bit more comfortable with LaTeX, and you've gained some insights into how I as a tutor, and more generally speaking, any of the tutors in this class would tackle the type of problem that you guys might see on a homework or an exam. So let's go ahead and click this template button on the course website and load into this busy and potentially intimidating looking web page for those of you who are not familiar with overleaf. Now, if this is your first time clicking the button, you will probably get a page that says you have been invited to join example homework DSC 40A Spring 2024. To continue to where I am, just click accept or agree. I'm not exactly sure what the button says. And if you need to create an overleaf account to do so, it is completely free to create an account, so do that. Now that we're all on the same page, or pages, I'm going to take some time and break down what we're actually looking at before I jump in to solve a problem. On the left half of the screen, we have the homeworkexample.tex file open. This is a LaTeX file, and all of the writing you see here is in a language called LaTeX, which is very commonly used in math and engineering and physics to write nicely formatted mathematical notation. On the right, we see the rendered version of the LaTeX that is on the left. Now that might be a little confusing, but let me give you guys an example. On the left here, we see this chunk of text that begins with squiggly bracket, \color blue, \text BF. This is not a real homework assignment. The two problems below are \text IT, not required. On the right, we see very similar text, but instead of \color blue and \text BF, we see blue bold font text. So what is on the right is a rendered version of the LaTeX that is on the left. I hope that gives you a little bit of intuition into what is going on, and we'll have more experience with this as we keep working with the problems. Now, a couple more things before I begin. Some of you might notice that there is another file here, DSC problemset.sty, and really this just dictates the style for all of the overleaf projects that we have in the data science department. As far as you guys are concerned, this may as well not exist. You'll never edit this file, you will never be working with this file, so you don't need to worry about it. A couple other things. I can't actually edit this file. I can press delete, I can do this, and nothing actually happens. That is because in order to edit this file, I have to make my own copy of it. And I can do this by going to Menu up here in the top left, clicking it, and going to Copy Project. I can name this whatever I want. I'll name it Jack's Example Homework because I'm Jack. It would be a little weird if I wasn't Jack and I did that, but luckily I am Jack. And when I click Copy, I will be loaded into my own version of the overleaf project that I have full edit access over, full control over. I can delete words and add them back in and have total control over what is in this file. Two more things. First, we have this toggle to show solutions or not near the top of our document. And you'll see that this says \show SOLN true. This controls the visibility of these, if I can highlight it, nice, these solution boxes, this one and the ones below it. If I change this to false, these solution boxes would disappear. Now you might be wondering why they're not automatically disappearing, and the answer is because we need to recompile our file. which is just a fancy way of saying we need to update the right half of the page so that it reflects the changes we made on the left half of the page. And we can do this by clicking the recompile button. We can also press, as you can see in the little hover thing, Command Enter on Mac. You'll see that this is compiling, and then the solution boxes disappear. If I change this back to true and press recompile again or Command Enter on Mac, the solution boxes will reappear on the right half of our screen. And this sort of relationship between the right half of the screen and the left half of the screen is true no matter what edits I make. If I go down to this is not a real homework and I delete the word this, it will not be updated on the right half of the screen unless I press Command Enter and recompile the right half of the screen, our text file. And last, before I jump into the problem, the avocados that are present directly to the left of the beginning of the problem signify the difficulty of the problem. One avocado is a relatively simple problem. 2 avocados is a little bit more difficult. And lucky you guys, the problem we will be solving has a 6 avocado part, which is quite a challenging part. Okay, let's jump into solving one of the problems. I was assigned problem 2. As you see, it says Jack's question. Once again, I am Jack, the protagonist of this video, and I will be walking you through this problem. Now, to help you guys out and save you guys from watching me write a little bit of the solution, press compile, write a little bit more, press compile again, and generally have this very staccato feel, I took the important parts of this problem and I put them into this other editor called hackmd.io that live updates what I type. So if I say Jack is a great tutor and he deserves a cookie, you'll see that this is updating live on the right without me needing to compile anything. And similarly, if I write LaTeX, which I can do by putting $signs around some math notation, this also updates live on the right half of my screen. It's important to note that there is no other magic to this. All of the code that I write on the left half of the screen would also work perfectly well in the overlay file that you guys are provided. The only reason I'm doing this is so that you guys can see what I'm typing in live time. Okay, cool. We can start now. At the beginning of this problem, we're given some properties of logarithms. I believe these are introduced in Math 20A or Calc 1, and 20C is a prerequisite for this class, so I'm not going to spend any time going over these properties. I'm going to take them for granted and be on the lookout for opportunities to use them in the problem ahead of us, which is Billy, the avocado farmer turned waiter turned Instagram influencer that you're all too familiar with, is trying his hand at coming up with loss functions. He comes up with the Billy loss, L sub b of h and y, where L is the loss function and sub b is because it's the Billy loss. And it's defined as the log of y over h all squared. Throughout this problem, we will assume that all y's are positive, and you can think about why that is. For the first part of this problem, we're supposed to show that the derivative of the Billy loss function is negative 2 over h times the log of y over h. So let's break this problem down and talk about how I would solve it. First, and the very first thing I would do, is simply substitute in the Billy loss function for its symbolic representation on the left side of this equation. So in LaTeX, I can make this nice little text block using $2 signs, and that will make all of the text I type centered in the middle of the document. To write this, I will do a fraction, which I do like this, \frac, and the first set of curly braces will contain my numerator, and the second set will contain my denominator. And this is, of course, with respect to h. And I'm rewriting the Billy loss function, which is given to me up here as this beautiful piece of LaTeX. So just to quickly walk you through this, and I will be walking you through kind of less and less stuff and holding your hand less and less as we walk through this, but to walk you through what this is saying that we have a left square bracket, then we have a log, a left curly bracket. This is another fraction where the numerator is y and the denominator is h. Then we have a right parentheses, a right square bracket, and we square this entire function, and that is just the Billy loss function. So I could break this log into the log of y minus the log of h. However, squaring that seems very intimidating, and I would much rather work with simpler terms that aren't squared. So intuitively, I want to think of a way, as a first step, to get rid of the squaring outside of our Billy loss function. And those of you who are familiar with derivative calculus may recognize that this is an opportunity to use the chain rule. And so I will do just that as a first step, just to try to get things as simple as possible and avoiding squaring different logs. I'm just going to use the chain rule and turn this into a more simplified version that still is equivalent to the same thing. This is still equals, and what this equals is 2, and I'm using c dot, which is the way to do this nice multiplication symbol. And if you're familiar with the chain rule, you know that it is 2 times the function itself, and this is multiplied by the derivative of what is on the inside of the function, which will just be the derivative of log y over h. I hope that makes sense to you guys. That is just some derivative calculus, and as a first step, it looks great as a way to simplify our problem into more attackable, bite-sized pieces. Now let's think about the intuition for the next step. This 2 looks pretty good to me because we have a 2 in our final answer. So it makes sense that we can kind of leave that alone. Similarly, this log of y over h also appears in our answer. So I think for now it's safe to leave those alone. Now, what doesn't appear in our final answer is any derivative. No derivative appears in our final answer, and so probably what we should focus on is breaking down this derivative or even taking this derivative to get rid of it. Now, how can we do that? I guess we could take the derivative of log of y over h by itself, but another thing we could do is use a log identity to break this down into even simpler terms and make it even more approachable. Now, this log identity is, of course, and I will show you guys, that the log of a fraction, so the log of a over b, is equivalent to the log of a minus the log of b. This breaks things down into very simple terms, especially when we're only taking the derivative with respect to one of the variables. And I will show you what I mean in a second. For now, let's just try this step and see if we get anywhere with it. So again, this is equivalent to, this times the derivative of, and instead of having log of y over log of h, we have the log of y minus the log of h. Again, that is just an identity of logarithms, and that should make sense to you guys how we get there. Now, let's actually look at what this is. The derivative with respect to h of log of y minus log of h is the same as the derivative with respect to h of the log of y minus the derivative with respect to h of the log of h. For those of you who pay close attention, the derivative with respect to h of the log of y is simply 0. The log of y is a constant with respect to h, and so we don't need to worry about this term at all anymore. All that we're worried about is the derivative with respect to h of the negative log of h. If we refer back to our properties of logarithms, we see that the derivative of the log of x is 1 over x. And so the derivative of negative log of h is negative 1 over h. This means that we can rewrite this entire derivative as simply negative 1 over h. To quickly recap that logic, what we did is we distributed this derivative. So we have the derivative of the log of y minus the derivative of the log of h. We've realized that the log of y is constant with respect to h, and so the derivative of the log of y with respect to h is 0. And the derivative of negative log h with respect to h is negative 1 over h. So let's write that. Again, we can kind of copy down this code from above, except this time we're going to replace this whole derivative with just the fraction, which we can write with, again, frac negative 1 over h. If we multiply this 2 by the negative 1 over h, we actually get our final answer, which I can write, which is right here in the problem statement, negative 2 over h log of y over h. Let's move on to part 2. Show that the constant prediction h star that minimizes empirical risk for Billy loss is h star equals y1 times y2 times all of the y's all the way to yn to the power of 1 over n. Okay, let's again attack this problem. First, let's write the formula for empirical risk for this problem. So we have r sub b, which I can simply say is the risk function for Billy loss, the same way as L sub b is the loss function for Billy loss. And we know from lecture that this will be equal to 1 over n, or the average of the sum. And this is how to write a sum in the tech. We have the sum from I equals 1 to n. You can see this summation appearing over here. And what we're taking the sum of is our Billy loss function. So we are summing over the log, the log of y sub I over h. And of course, we're squaring this log. And again, this is just the definition of what a risk function is. And I'm just writing this out so we can see our starting point. So in this context, to minimize the risk function, what we often do is we take the derivative of the risk function and we set it equal to 0. And we also saw this in lecture as well. So combining that knowledge with how to find the optimal prediction with the knowledge of what we did in part 1, let's see if we can break this problem into a smaller part, a more approachable part, and answer it correctly. So we have the derivative with respect to h, of our risk function is going to be equal to the derivative of 1 over n times the sum from 1 to n of log of yi over h squared, which is again simply the average of the Billy loss function for all of our data points. We have to take the derivative of this as well, which we can simply write inside of the summation. We can just write it like this, d dh, because when you're taking the derivative of a summation, it doesn't matter whether the derivative is outside of the summation or inside of the summation, because you're just working with addition. Now, taking what we know from part 1, we know that the derivative of the Billy loss function is actually just negative 2 over h times the log of y over h, which we can put in this and simply substitute y sub I for y. So let's do that. Let's put this down here. We're going to get rid of the derivative, and we're going to substitute what is inside the summation for this negative 2 over h log of y over h. And this is just, again, simply substituting in what we just proved in part 1 for the derivative of the Billy loss function. Cool. To take this a step further, negative 2 over h is a constant. When we're summing over I, so we're going to be iterating through, oops, I'm sorry, I didn't substitute in I here. This is y sub I over h. That's very important because we're summing over I. But to get back to what I was saying, when you're summing over I, negative 2 over h is just a constant. It's not going to be changing. And so you can factor that out and multiply it back in whenever you want. So we can write this, and I will just be doing this one step at a time. We can rewrite this summation as the fraction of actually negative 2 over nh, and get rid of this fraction. So we just move that fraction outside of the summation, and now all that we are summing over is the log of y sub I over h. This step allows us to do something very cool when we think about what minimizing empirical risk actually looks like. As I mentioned before, what we often do is take the derivative of the risk function and set it equal to 0. Let's do that now and see what happens. If we now multiply both sides by the reciprocal of this fraction, which is to say that we multiply both sides by nh over negative 2, we can actually just completely eliminate this constant from our formula, giving us something that looks like this. Oops, this. This is a huge step forward in simplifying this problem and reaching a solution, and it came just from setting the derivative of the risk function equal to 0 and factoring out as much stuff as we could from the summation. Again, there's no magic to this step. It really is just trying to make the problem as simple as possible. Further, this allows us to greatly simplify our problem again by using the same trick that we used in problem 1 to separate our log into two bite-sized pieces. This again is the identity that says that the log of a over b is equal to the log of a over the log of b. Let's rewrite this log in that way. 0 is equal to the sum from I equals 1 to n of the log of y minus the log of h. And I'm sorry, but this is y sub I. And we could write this whole thing in parentheses, but we could also write this as two sums, like this. And this is because when you are summing over two things that are being added together, it is the same as summing them separately and then combining the sums. This is very important because expanding both of these sums independently actually gives us a very simple equation. I will show you this one expansion at a time. First, let's expand the summation of log of y sub I. If we get rid of the summation, what we're left over with is the log of y1 plus the log of y2 plus all the way to the log of y sub n. Second, if we expand the right summation, we actually get something very interesting. This is because the log of h actually doesn't include any I, which is to say that the log of h doesn't change depending on how we are incrementing I. So each time we have an I, so I equals 1, I equals 2, I equals 3, all the way to I equals n, we will simply be adding another log h to our summation, which is to say we will have log h plus log h plus log h plus log h n times. Or in other words, we will have n times log h. And I will escape this log. Or just n log h. Now this is a really beautiful equation, but if you're astute, you will realize that this log of y1 plus log of y2 plus all the way to the log of yn is one of our identities, which is that the log of a plus the log of b is equal to the log of a times b. We can use this logic for this entire summation right here and rewrite that entire first part of our equation as simply the log of y1 times y2 all the way to times yn. And we are still subtracting n log h. Now, it may appear that we're at a little bit of an impasse because it's not exactly clear what we have left to simplify. But luckily, we don't have to simplify this any further. The important part of this problem is that we are trying to solve for h when we set the derivative of our risk function to 0. I mentioned that at the beginning of the problem, and again at some point in the middle, and now I'll mention it for a final time, that the way you can solve for h star is by setting the derivative of your risk function equal to 0 and solving for h. So let's move the n log h to the other side of the equation and see if we can take any steps from there. So instead of 0 here, now we'll have this n log h on this side of the equation, and it will of course be positive. It will not be a bullet point. Let's look back at our log identities. Right here we see that the log of a to the c is equal to c log of a. And of course, conversely, that c log of a is equal to the log of a to the c. Well, down here we have a c log a. In fact, our c is an n, and our log a is a log h. So we can rewrite this in the following way. We can write this as log of h to the n is equal to log of y1 times y2 all the way to yn. And now, since these are both logs, we know that h to the n is equal to, if you'll excuse me, y1 times y2 all the way to yn. So you recognize that raising both sides to the power of 1 over n actually gives us our answer, and we can write this as h star is equal to this product raised to the power of 1 over n. And this is, of course, what we were trying to get at the beginning of this problem. We were supposed to show that the constant prediction h star that minimizes the empirical risk for Billy loss is y1 times y2 times all the way to yn to the power of 1 over n. And after all of these steps, we did just that. Now that we have solved these problems, let's copy and paste them back into the Overleaf document to show that everything I typed also works in Overleaf. I'll take this and put it at the solution, begin your solution here. And I will take my solution to the first problem, and I will put it to the solution in here. Let's recompile. And here we can see both of our solutions in beautiful rendered LaTeX in the PDF rendering of our homework example.tex file. And we are done. I really hope that this walkthrough provided some insight for you guys. I hope that it made you a little bit more comfortable with Overleaf and LaTeX, and I wish you the best of luck on the class. I look forward to meeting you all in discussion and hopefully my office hours, and do not hesitate to reach out with any questions. Thank you guys so much.